optimization. So not everything in life is a shortest path problem or a constraint satisfaction problem. There do exist other kinds of problems, like the traveling salesman problem and stuff like that, which are called combinatorial optimization problems. And they're very similar to constraint satisfaction problems in that you get the number of decisions up front. Like everyone knows the traveling salesman problem. You have a bunch of cities. I think I already drew it in a previous class. You have a bunch of cities, and you know the distances between them, and you want to find the cheapest way of visiting all the cities. And you may say, like, we don't have traveling salesmen anymore. We buy things on the internet. Okay, you buy them on the internet using a computer. And computers are made by having a board into which you place chips. The chips have little pins that go into little holes on the board. The holes are not made by little elves. They're made by a drill press, which has to go visit all the holes on the printed circuit board. You want to minimize the number of drill presses that you buy. Therefore, you want to maximize the throughput of each drill press. We'd like to find the fastest way of visiting each location where we need to drill a hole with the head. It's a traveling salesman problem. When I was in grad school, a fellow grad student of mine proved that optimal register allocation in a compiler is completely equivalent to the traveling salesman problem. Like, people come up with these crazy equivalences. If you took the algorithms class and you know about NP completeness, you know that of the great oneness of all interesting problems called NP completeness. So anyway, TSP actually does come up, amazingly. So this is a combinatorial optimization problem. You have lots of different combinations of options for the different variables to take on different values, like what city am I going to visit first? What city am I going to visit second? What city am I going to visit third? For any complete assignment of values to the variables, we have a solution. And the solution has a cost. So like every tour that visits all the cities has a cost. And you want to find the least cost goal, the least cost leaf in this tree, this fixed depth tree, this depth bounded tree. So that's combinatorial optimization. It's a lot like constraint satisfaction, except instead of any goal being okay, having a very binary, like it satisfies the constraints or it doesn't. Here we can talk about how costly is it. So in fact, in the real world, some problems are constraint satisfaction problems, but sometimes people talk about max CSP problems, which is, I can't satisfy all the constraints. It's like my life. I can't satisfy all the constraints. I want to find a solution that maximizes the number of constraints that are satisfied. Like, you know, I can't do everything. I just want to do as much as I possibly can in the time I have. That's called max CSP problem. It's a combinatorial optimization problem. So that's what combinatorial optimization is. What search algorithm would we use to look through the tree for a good solution? A star. Why would you say A star? Because we want to find a least cost goal, and that looks a lot like this line here. Yeah, I want to just point out this line here. Max depth. We have a maximum depth. Now, to be perfectly frank, there are combinatorial optimization solvers that use an A-star-like strategy, so it is used a lot. The vanilla way to approach a combinatorial optimization problem is depth-first search. But people do use, the most famous solver in the whole world is called Cplex, and it uses something very much like A-star. So that's not actually a bad answer, but it's not the one I was thinking of. Most people use depth-first search. Now, I'm only going to talk about two algorithms for combinatorial optimization. One is hill climbing, which I already talked about in the context of shortest path problems. But you can also think about doing. I want to show you a different way of thinking about hill climbing. So when I was talking about hill climbing before for shortest path problems, I said you generate all the children, you take one of them. You forget about the others. You generate all the kids, you take the best one. At each of those times, I was instantiating an additional action in the plan. All right? I look at all my kids. Normally when we're doing shortest path search, each child represents adding one more action to the plan. So hill climbing was running down the tree, adding yet another action to the plan until we got to a goal. There's another way to think about hill climbing in the situation where we have a fixed number of decisions. If we have a fixed number of variables, a fixed number of decision variables, then I can think like this, and this is a crazy way to think, but it turns out to actually work. I can think of having a complete solution written down. A solution is just a vector of assignments of values to variables. I can have a complete solution written down, and in most combinatorial optimization problems, like that is a legal solution. Like that's a legal tour. It's a legal traveling salesman tour. It might not be the optimal one, but it is a tour. I can think of what are all the ways I could modify this tour to change it. Potentially make it better, potentially make it worse. You know, I could change the order in which I visit a couple of the cities. And every change results in a different solution. It may cost more, may cost less, and there could be lots of these neighbors, of these neighboring solutions that are very similar, but they differ in some way. We've changed the initial solution somehow. This is a very different kind of search than anything we've talked about so far. This is also called iterative improvement search, because you have a complete candidate solution and you're just trying to improve it. So hill climbing in this context corresponds to looking at your neighbors and seeing, is there someone who's better than I am? Is there a way I can improve this current solution? And if so, move to that solution and make that the current one. And then look at a way to improve that one. So people often talk about a picture where if we line up all the solutions along the bottom here, each one of them has a cost. Right, so I actually have a kind of fitness landscape people talk about, and if I'm doing something like TSP, I guess lower is good. So if I have a solution that's here, I look at my neighbors, and I say, oh, you know, are there any similar solutions? Is there one of them that's better? And oh yeah, that one's better. And then I test its neighbors, and I say, oh yeah, I can make that even better. Oh, I can make that even better. Until I get down to here, and I check my neighbors, and oh no, all my neighbors are worse. That's called a local minimum here. I'm trying to minimize cost, but I can't think of a small change to make my solution any better. So these local improvement algorithms suffer from local minima. So there's a whole industry of people trying to come up with algorithms that can get out of local minima efficiently. And I list some of them on the next slide. Simulated annealing, where you bounce around, you pretend you're a little excited atom and you bounce around the search landscape. Genetic algorithms fall into this category, and that's really why I'm talking about combinatorial optimization at all. Is a lot of people associate genetic algorithms with AI. A genetic algorithm uses a crazy neighborhood function. So instead of just having a single solution and modifying it, a genetic algorithm actually has multiple solutions. And if that guy's hatched that way and that one's hatched that way, the neighbors would be things like, oh, here's a solution where I take the first part of the top solution and then take the last half of the bottom solution. We've done crossover between the solutions. Right? Maybe I try that solution too. So that would be a potential neighbor. Potential when I could have another potential neighbor where I choose the crossover point in a different place. A genetic algorithm is just a different way of exploring the space of possible solutions. But it's interesting because it has more than just a single current solution. Usually there's a whole population, and you choose two solutions that look like they're good and try and combine them somehow. Everyone understand that? Okay. So that's as much as I want to say about combinatorial optimization for this class, but it's good to know about. One nice thing about these methods like hill climbing and simulated annealing, and yet for some reason this is called hill climbing even though most people go down the hill. I don't know why. The nice thing about hill climbing and simulated annealing and genetic algorithms is they're really broadly applicable. All you have to do is be able to say, how much does the solution cost? How can I change it? And you can immediately apply these algorithms. If you want to apply a CSP algorithm, you have to think, what are the constraints? How do I propagate them? How do I do forward checking? All this complicated stuff. These, it's like very simple. I have a solution, I modify it. I have a solution, I modify it. Can I make it better by a little small change? So they're very easy to apply. I think I mentioned the first day of class that General Electric used AI to design the turbine blades of the engine for the 777 aircraft. The program they used was a GA. They used a genetic algorithm, and it came up with a turbine blade design that no one thought of. It's like crazy, but it worked super well. So for them, the solution is like the shape of the blade, and I don't know how they represent that, but maybe a bunch of splines with points, and they modify where the points are, and that changes the shape. And then to tell how good a solution is, they run it through a turbine simulator. So it's like sometimes just telling how good the solution is, it can be a complicated thing, like they run some big fancy program. But if you've got time and a supercomputer, like you can run a GA on an aircraft blade design. Okay. Any questions about combinatorial optimization? I just wanted to mention GAs, since everyone's heard of them. A lot of people have heard of them.